Hello and welcome to Coffee and Control, the podcast where I find fascinating people from within the world of control and convince them to answer all of my questions. I'm your host, Lucy Hodgins, and my guest today is an assistant professor at MIT. This guest was mentioned right at the end of the interview that I did with Alberto Paduan back in the summer, and I started reading through his thesis, and it legitimately took me about one paragraph to be like, I absolutely need to interview this guy. The rest of his thesis did not disappoint. It was beautifully written, very mathematical, but also really accessible. Fortunately, he agreed to be interviewed at CDC back in December, and he was so excited and enthusiastic about his work when I was talking with him. It was amazing. So get ready to hear all about the theory and intuition behind the co-design framework, including its links to category theory and how it can be applied to designing autonomous vehicles, mobility on demand systems, multi-agent robotics, and pretty much every system you could ever think of, with my guest this month, Professor Gioele Zardini.
My name is Gioele Zardini. I am originally from the south of Switzerland, a very weird place because it's a cultural limbo. So you essentially are raised as an Italian person, but you're not really. But then when you move to the German or the French part of Switzerland, you also don't belong there. So we are kind of in a cultural limbo, not enough Italian for the Italians, not enough Swiss for the Swiss. But I'm Swiss. My research, broadly speaking, is about solving large decision-making and optimization problems with societal implications. So things like, how do I design an interconnected mobility system? How do I design a bunch of robots given a task? And how do I do that by, for instance, maximizing performance, minimizing energy consumption, minimizing mistakes or errors? So multi-objective, multi-component, interconnected system design.
Okay, so your PhD examined co-design of complex systems. The thesis was extremely impressive. I'm going to ask you a load of detailed questions about that throughout this episode. Firstly, I'm curious as to how you ended up doing this PhD in particular.
Yeah. So I think this is a good... last year, I also got one of these PhDs in control interviews, and I explained this there as well. So when you read the thesis, it's, of course, I'm proud of the work, but you always stand on the shoulders of giants. So my biggest gift was to work with advisors, specifically Emilio Frazzoli, Andrea Censi, and Marco Pavone at Stanford and ETH Zurich, that gave me freedom and also had big visions themselves. So they essentially taught me to dream big and to not be constrained to small or fancy problems, to dream of something that people are not doing. Co-design is it's a framework for holistic design of complex systems. And you're right, how do you get there? So I did my undergraduate studies in mechanical engineering with a focus in controls. And then I did also my master's in that domain at ETH Zurich. And in between, I spent a year in Singapore working for an autonomous driving company. Back then it was called Newtonomy. It's the company that my advisor, Emilio Frazzoli, co-founded. And I had spent also some months at Stanford visiting Marco's group. So I had done some experiences. And essentially every project I worked on was focusing on a specific system with very well-defined interfaces. Like my first bachelor thesis problem was working on, essentially Brad Nelson back at ETH Zurich gave me a robotic arm and said, okay, we should use it. We bought it, so we have to do something with it. Build a robotic hand, attach it to this sensor, and make it do something cool. Like, I don't know, pouring a glass of beer or something like that. And this was pre-manipulation hype. So this was 2016, 17. So right now, when you go to a robotics conference, everybody's doing manipulation. There are all the machine learning things. There, it was not really the case. And so that thesis was all about coming up with the design, mechanical engineering, so a lot of CAD, coming up with the sensors, understanding the signals, and then designing a controller that, given the measurements, was closing the end and doing some stuff. That was a very specific thing. Then I did my project with Emilio. At ETH, there is a thing called semester project. It's kind of a thesis that allows you to explore more practical projects. And there I worked with event-based cameras. So it was about doing control and perception for this new kind of sensor that later on became very famous, in part because of people like Davide Scaramuzza, who essentially rediscovered computer vision for this new kind of sensors. And there I focused on that. And then At the company, I was more working on automated calibration, automated decision-making for autonomous vehicles. But at the end of the day, I was always feeling kind of limited by the nature of the problems I was working on, in a sense that everything was always well-defined. There was a clear baseline. And it wasn't clear to me how my component I was working on could fit in a broader system. And so when I was looking for master thesis projects, I really felt, hey, I need to think about the broader impact of this technology. In this case, autonomy and robotics and so on. And back then, I guess still, but back then the real killer app of autonomy was autonomous driving, right? So it was the closest to be still interesting from a research perspective, but also almost ready to be deployed. Not quite. When I moved to Singapore in 2018, Autonomy was the first company that was testing on public roads. So we had a neighborhood called One North in Singapore where you could actually test your algorithms on the vehicles. And that was pretty cool back then, right? Because you could literally go on roads where other pedestrians were there. It was not a fake, company dedicated road. These days, people that might listen to this podcast say, oh, well, but in San Francisco and Phoenix, I have these vehicles. In London, I have other companies. But back in 2018, this was not the case, right? So I think that was cool. But I was looking for an impact of this technology, so beyond the single vehicle. And so I had discussions with Emilio, and Emilio, one thing he does very well, and I think I was very lucky in finding an advisor that lets you go and opens you doors, was, hey, you should go with my student, Marco Pavone. Marco is a professor at Stanford, but was Emilio's student. You should go to Stanford and work with him. He's working on this impact of single vehicles on larger fleets, controlling this so-called autonomous mobility on demand systems, right? And he's looking at the impact on public transit, on society. So I think you will find it as a good experience. So I went straight from Singapore to Stanford. And there I had a blast. Essentially, I started seeing this research on multi-vehicles, how do you design the fleet size, how do you design the network? I guess we'll go into the details of this. And I started also working closer and closer to Andrea Censi, who was at ETH Zurich. And the idea was, let's use this co-design framework, these co-design ideas that Andrea had. Andrea was at MIT before and started developing this framework for automating the design of complex systems. And I think the mobility case was something he didn't think about back then. Initially, was only focusing on a single robot. But I think as soon as we had a couple of discussions, it really resonated with him and said, yeah, we should try to apply this thing. And so I was at Stanford working with Marco and Andrea. And that was the first pure research experience I had, right? And since then, I got in love with the problem. It's a huge problem. You cannot possibly solve it in 6 months. Yet I think I will dedicate the next 20 years of my research group probably to solving that. And that's how I got to working on the holistic thing. So, okay, probably this is going to be a leitmotif of this podcast. You will ask a simple question, I will diverge. But the very short answer is, I worked on single components. I was frustrated because I couldn't see how they could interact and impact a larger system. And so I said, okay, I have to take a holistic perspective. How can we do it? And I think later we'll come to systems engineering, but I think a key aspect is coming from controls. I also wanted some formal framework to deal with this. And these days, when you go and look at systems engineering traditions, there's a lot of this holistic perspective, a lot of these interconnected systems, but there's not a formal framework that deals with this. So I think coming from controls was really helpful in essentially developing my taste for what a good framework could be. And from there, I started working on co-design. Yeah.
So in terms of your PhD work, firstly, a very basic overview. What is co-design and why is it important?
Yeah. So what is co-design? Co-design is a modeling and optimization framework to first formulate interconnected design problems and then solve them. And I'll start with an example. Imagine that you want to automate the design of a vehicle, an autonomous vehicle. Here you have to make decisions at a lot of levels, right? You have to design the controllers. You have to decide which vehicle you want to automate. Is it an SUV? Is it a small vehicle? What kind of dynamics does it have? You have to choose the compute. You have to choose the sensors, where to place the sensors, but also how to use perception algorithms to use the sensors. You have to use resource allocation algorithms to understand which component or which compute should be executed when. So there is a huge architecture, both physical, hardware, software, and things in between, like there are liability, ethical concerns, right? And when you try to design such a system, and this is just a single vehicle, but when you want to design such a system, there are many challenges. The first challenge is all these components come from different disciplines. Typically, people model them using different languages. And in my talks, I always have this picture of an engineer sitting at a therapy session. And the first reaction is to say, oh my God, I cannot solve this. Like it's impossible. And not only I cannot solve it, but I have no clue how my designs for the specific component will affect the entire system, right? So the diagnosis is, okay, we lack something that allows you to do formally, but also intellectually tractably design or specify design and solve design problems. So that's one challenge. The other challenge is, as I was saying, many of these systems lie at different abstraction levels, not only different communities, but also totally different scales. I could be designing a sensor for an autonomous vehicle. Then I could be putting together components to form an autonomous vehicle, but then I could be putting vehicles together to form a fleet and now solve control problems for the fleets, but also have to make sure these fleets interact with whatever infrastructure already exists in a city. So when I have to design a single technology, I have to consider all of these layers, right? And they are really diverse in the way they interact and the way they are modeled and so on. And the final challenge I always mention is you are not always designing everything, right? There are stakeholders and people have different objectives, different languages. So imagine designing a mobility system in Rio de Janeiro. It's not only about us, the control community designing the technology, but it's going to be policy, it's going to be insurance companies and so on. So there are these weird interactions between people that speak different languages, all the way from theorems and proofs to Excel sheets, if you're lucky, or even traditions of why something works and why not. And so whenever you need a language, you need to take care of these three challenges.
Just to summarise, 3 challenges of designing complex systems are, firstly, the components of your design may come from different disciplines. Secondly, they may exist at different levels of abstraction. And finally, they may be external stakeholders present with differing objectives.
Co-design is, I believe, I know it's a strong statement, but it's the first framework that deals with all of these challenges in a intellectually and computationally tractable way. When I say intellectually tractable way, I mean that not only you're able to formulate these very complex optimization problems and solve them, but also you're able to contribute as a non-technical expert, right? You want to avoid the situation where you kind of need these so-called system architects that are people that are highly trained, they know everything about the system, and they are the only ones that can manipulate these problems. In a sense, co-design allows you to do this in a distributed way. And I think that's what co-design does. What co-design also does is it leverages some so-called compositional theories in the background. So what the user will see is a framework for optimization, exactly as you might know CVX for convex optimization, or you might use interfaces such as Gurobi or these kind of things. But in the background, we're using magic mathematical concepts coming from applied category theory, right? And that's what gives it all these nice compositional properties, the generalization properties, and so on. So in a nutshell, co-design is the first multi-objective, multi-component systems engineering optimization framework.
If you're eager to know more about the magic of category theory, do not fear, because we will be returning to this a little later in the episode. But first, we've got to lay down some co-design basics. In particular, a foundational concept of the co-design framework is that of trade-offs. So to quote Gioele's thesis, trade-offs characterise all engineering disciplines and can be found literally everywhere. This is then followed by a footnote stating everywhere in this thesis, everywhere in your field, and everywhere in your daily life, which leads to the question of how does one formalise these trade-offs?
So there are a few foundational concepts I wanted to cover first. So one of them is that of a poset. So what is a poset and how can these be used to characterise trade-offs between quantities?
All right, I always like to make this example. So first of all, poset is an acronym for partially ordered set. And let's make an example. So do you prefer pizza or burgers?
Burgers.
Okay, so you have let's say people in the audience don't know, but I'm drawing. So you have burgers. Oh yeah, no, it works. Burgers over pizza. Okay, now I have to ask you: do you prefer fish and chips or burgers?
Burgers.
Oh wow, so you are not a real British person, I guess.
No.
Okay, so burgers on top of fish and chips. Do you prefer fish and chips or pizza?
Fish and chips.
Or are you sure? Or you can also, you're free to say it depends, right?
I'm not very good at making decisions. We're going to say that either.
Okay, let's pretend you don't know, right? So in a so-called total order or totally ordered set, you always have to make sure that whatever your preference relation over a set is complete, in the sense that there is always a relation between any two elements, right? So in a sense, you form a so-called chain. In a partial order, you allow a degree of freedom, which is some of your elements of the set might be not comparable. So in your case, you like burgers over anything else, but pizza and fish and chips are not comparable, right? Example of total orders are things you can enumerate. If I want to know the number of vehicles in a fleet, those are positive natural numbers, and it's like 1, 2, 3, 4, 5, and those are always ordered with respect to each other. If I have the monetary cost for certain equipment, that's going to be a total order. It's a positive reals. If I have sets of people at the conference, this could be made into partial order, right? Because it could be you and me and me and John Doyle, and these two sets are not comparable, right? Because they don't include each other. But there might be another set including Florian Dörfler, you, me, and John Doyle, which includes all of us, right? So in that sense, all the sets I told you before are included in that larger set. And so you can create these order relations. So this is the intuitive explanation. The formal explanation is a partial order set is a relation with special properties. There are three properties. One is the relation must be reflexive, meaning every element in the relation is related with itself. Another one is transitivity. If I'm related with you and you are related with someone else, I have to be related with that someone else. And there is another one which is called anti-symmetry, which says that if I'm related with you and you are related with me, then we must be the same thing. We must be equivalent. There is a slight different notion, which is the notion of pre-order. When you allow two things to be related bidirectionally and not be the same, and then you say they form an equivalence class, right? So for instance, I could say every person that is 30 years old, they're not the same person, but they belong to an equivalence class of people that are 30 years old. In a partial order set, these people have to be all the same element in the set, right? So that's the thing. And in co-design, partial order sets are the objectives or the specifications. Everything we will talk about will be, I want to maximize demand satisfaction, and you order the demand distributions in a certain way, and you want to minimize, emissions, and you order the emission in a certain way. So it allows us to be quantitative when thinking about design.
The next key concept is kind of representation of design in terms of implementation, space, functionality, and resources. Yes. So how can functionality and resources be represented as a POSE set, and how does this allow you to construct your design problem?
That's a very good question to understand co-design. You can think about what we call a design problem or a component selection problem as essentially a relation between three spaces. There is the thing you're designing, the choice you're making, which is the implementation space. This could be you're choosing a parameter in an algorithm, you're choosing the algorithm itself, or you're choosing the vehicle you want to use in your fleet, whatever design decision you have. Typically, these exist because they provide a functionality. We call it functionality, but you can think of it as a specification or a desired behavior or whatever you want to achieve. And providing these comes at a cost, which we call resources. But you could see these as requirements, you could see these as assumptions you have to make on the problems, and functionalities could be guarantees that you have at the end, right? The way you order these things is, as I told you before, in some cases, they're going to be totally ordered. In many cases, you will not know, right? So, for instance, if you say, I want to serve a certain demand, and you think about the demand as origin-destination pairs and some specifics about people, you might have sets of origin-destination pairs in a large network, and these sets may not need to be comparable necessarily, right? So in that case, you might have a partially ordered set, and then your cost could be the total emissions and travel time in the system, for instance, right?
So a particular implementation will provide some functionality at the cost of resources, and these functionality and resources are arranged into some partial order. The question then becomes how to represent mathematically the relationship between functionality and resources for a particular implementation. Some of the terminology Gioele is about to introduce does relate to category theory. We are going to return to this a little later on, but for the minute, just try and focus on the intuition.
So how these three spaces are related is very special. This is the entire definition of what a design problem is. Essentially, a design problem is a map. So the map is, I can formulate it very precisely. It's a map from fop times r to bool. So functionalities with an operator that's called op Cartesian product with resource space that maps into bool. Bool is a special partial order which only has true and false and a single relation. And to give you a very quick intuition, what this map does is, given any pair of functionality and resources, so given any pair of desired behavior and budget you have available, it answers the question, does there exist a design in my design choices that gives me at least what the functionality I want? Remember, you want to maximize those by requiring at most the resources you have available, right? So you want to buy ice cream, you have some US dollars, you want to know if there is an ice cream shop that gives you at least the quality of ice cream you like by spending at most the budget you have available. That's what's called a design problem, but it's technically speaking, it's a Boolean profunctor, right? And this has a special property, which is it is monotone. So it's a monotone map in the sense that if, suddenly you require less functionalities, so you become less picky, that shouldn't cost you more. And on the other hand, if you're suddenly richer in resources, that shouldn't provide less functionality, right? And so this gives you a way to think about any component choice as a relation between its functionalities and resources. And it's very handy because you can use it in so many domains, right? In some cases, you might even have a formula that says, look, if you want this functionality, it's going to cost you these resources. In some cases, you don't have a formula. In some cases, you have things that are more, you have discrete choices, right? You have sort of a catalog of options you can choose from. Sensors you can buy off the internet. Some cases, there is a very complex process to assess whether some functionality resource pair is feasible or not. For instance, you have a simulator and you have to, every time you want to explore possible functionality resource pairs, you have to turn a crank of a simulator or run a neural network or whatever, right? So it is a kind of a universal way to visualize these relations. And it has very nice structure that, I guess we get to it later, allow you to solve these problems in a tractable way.
Okay, I guess the final question in this part of the interview is about the concept of a query in design.
Yes.
Could you explain a bit about this and also whether your approach to design differs depending on the query being asked?
Yes, that's very, very good question. So in my lab now, we're developing new queries that are kind of even more exotic than the classic co-design ones. But, we haven't talked about composition yet, but eventually we're going to take a lot of these boxes, a lot of these design problems, and interconnect them based on the needs they have, right? Because if I have a box that requires some things and another box that provided something, I can interconnect it. If I have two processes happening independently from each other, but I want to consider them, I have the so-called parallel composition, right? I could have feedback composition and so on. So the idea is that I can create a multi-graph of these problems. Where the nodes are the problems and the edges are the dependencies. Now, once you have such a big interconnection, first of all, we have a property which is every time you compose problems, you get something with the same properties again. So the property of being a design problem is compositional, which means at the end of the day, when I have this huge diagram made of various components, I can draw a big box around it and I have a design problem. And now I'm ready to say, okay, I can ask questions about these design problems. And the typical query is the following. I fix functionality at the system level. And, I want to find all the solutions or the optimal solutions at the single component level that allow me to minimize some resources at the system level. So let's make it very concrete. I want to design an autonomous vehicle. Of course, I told you there's going to be a component to design the controller, a component to design the planner, a component to design the perception, a component to design the compute, and so on. At the end of the day, when I aggregate all of these boxes, there's going to be some resulting functionalities. For instance, the task complexity. For instance, the environment I have to be robust to. And there's going to be some resulting resources, like the budget I have to invest, or the energy consumption, or these kind of things. The query there is going to be, let's fix a functionality at the system level. So let's fix some distribution of tasks, some particular environments you want to be robust to. And let's find all the optimal components in this diagram. So the optimal sensor, the optimal perception pipeline, and so on. That minimizes the resources. Let's say resources is time, it's performance, in, say, energy versus monetary investment. There's going to be a so-called trade-off space or a Pareto front, right? Or technically speaking, an anti-chain. A bunch of optimal solutions that are not comparable to each other, but that are optimal. And you want to find those. So that's the first query, which is fix functionality, minimize resources. You could ask the other question, which is, hey, I have some budget available. Can you find the best functionalities I can get out of this? So this is the opposite problem. I have people that say, hey, I can spend this amount of energy, this amount of dollars. Tell me what's the best thing I can have this robot do, right? And so going back to the ice cream problem is like, oh, I want some ice cream, find me the cheapest option so that I get this quality of ice cream. Or, hey, I have these dollars, find me the best quality I can get out of these dollars, right? Those are two queries, and they are dual in the optimization sense. So there is a nice relation between the two. But, a little spoiler for what will come next, when you start considering uncertainty, for instance, now the query could become, so you could ask very specific questions about what eventually happens to your distributions of design problems. So it could be, what's the probability of a solution happening in a certain way? What are some risk metrics, right? If now my resources and functionalities are temporal aspects, you might ask, okay, what's the optimal solution now? What's the optimal solution in 10 days? What's the optimal solution in a year? So you can make these queries much, much richer in detail, but the classic ones are the two I just mentioned.
For more detail on this, I refer you to a paper titled On Composable and Parametric Uncertainty in Systems Co-Design, which was written by Gioele and his PhD student Yujun Huang, who I got to speak to at CDC and was very lovely. The paper is quite maths heavy, but it is super interesting, so I definitely recommend checking it out if you would like to learn more.
Okay, so I guess we've talked a little bit already about like interconnections and building up complexity. So yeah, I think the next question I was going to ask is like, how do you interconnect different parts of the system? What are the constraints involved?
Yes, that's I hinted at it, but I'm happy to retake that question. So essentially, you can think of every design problem, every such Boolean profunct or feasibility relation as a box. And now you have boxes, it's like Legos, you want to interconnect boxes, right? So the easiest one to understand is what we call series composition. So it's like the resources required by a box are provided by another box. Let's have a simple example. There is a box that requires compute, and there is some chip that provides the compute. And there is a constraint in between, which is a partially ordered constraint. Essentially, that there are two wires. The compute wire is going to be a partial order. In this case, it's a positive real numbers. And you are saying, hey, the compute this process requires can never exceed the compute provided by this other component, which is the chip, right? So this is the first component composition, and it's called series composition. And again, as I said, composing two things in this way gives back a design problem, right? So the act of composing is a good thing. So the whole structure is closed under composition. There is the other one, which is parallel. So you have two processes happening in parallel, not necessarily in time, right? It's like you want to consider both, but they don't interfere with each other. And now you put them in parallel, and that's called the parallel composition. There are options in which you want to choose between two options. You might have ands or ors, right? Depending on whether you want to make sure every component satisfies some properties or at least one component satisfies some properties.
So what are the examples where you might use this kind of interconnection? So if you have two design problems modelling interchangeable technologies, in this case you can use the OR operator. On the other hand, if you have a design problem representing two slightly different models of the same process, you might want to ensure that both of these are feasible, and in this case you would use the AND operator.
And finally, you have feedback operators. And feedback is kind of different than the control interpretation of feedback. Here, feedback means irreducible complexity constraints. The very nice example is you have a drone, the drone has to fly, it requires an actuator. The actuators must be powered with a battery. The more power I need, the heavier the battery will be. The heavier the battery will be, the more actuation I will need, and therefore the more energy I will need, and therefore the heavier, and so on. So you have this irreducible feedback loop. Now, the nice thing, and the reason I say this is intellectually tractable, is you can really plug and play these boxes and interconnect them with each other at a graphical level. And you're sure that all the mathematics in the background works. And the reason why you can do that is that these diagrams are called wiring diagrams. And all the composition operators I just described arise from a categorical structure. So you can create a category of design problems. A category is a very special construct in mathematics that allows you to structure these compositional properties. Specifically, a category is made of objects, things that you want to compose, morphisms, So ways to go from one object to another. And then composition operators for these morphisms. And finally, a special morphism, which is called identity morphism, that allows you to go from one object to itself, right? Design problems are a special category where the objects are partial orders. The morphisms are design problems that allow you to move from functionalities to resources. And the composition operator is this series composition. All the other operators come from extra structure. Our category is not only a category, but it's also a symmetric monoidal category. Therefore, you can do parallel composition. And not only that, it is also traced. So it means it has a trace, and it means you can do a feedback loop. And many other things. We have much more structure, but essentially this background structure gives you all you need to compose these boxes at will.
So on a high level, the co-design theory involves grouping design problems together using wiring diagrams. These look very similar to block diagrams, but there's no direction of information flow. You're just connecting things together. We're going to come back to that point later. Now, Gioele has outlined a lot of technical details of category theory here. I'm going to leave links in the description if you want to learn more about it, but the core idea is that category theory gives a way to reason about design problems in a mathematically rigorous way.
And when we will talk about solution, it also ensures that you can solve these problems in a structured and tractable way. And having category theory as a formalism to deal with all of these things is also great when you want to expand the theory, because category theory gives you a lot of generalization properties. And so this is a nice plug for category theory as it's really been my love for the PhD. I started, when I started thinking about these things, I said, okay, what's the math to talk about composition? And then I found these books, one from David Spivak and Brendan Fong. It's called 7 Sketches in Compositionality. These two are great researchers that now are friends, and they started working on category theory for, they are applied category theories, but they started working on these books for broader audiences. And, I started reading this book, and by then it was clear, okay, we have to use category theory everywhere. It's so cool. And since then, we have created a class at ETH, which are now improved, and I'm teaching at MIT. We created workshops. Actually, we had a workshop here at CDC as well. So there is a big effort in converting the controls community to study more of these compositional tools, because I think it's really the future, and we need more people to think about those things.
Okay, so kind of sticking on the topic of feedback, but in a completely different context. So I know a few parts of your thesis have worked on or looked at how to incorporate control into co-design framework. So kind of on a broad level, how can control problems be formulated as a design problem?
Very good question. So indeed, one of my first PhD papers was showing that LQG control can be formulated as a bunch of design problems.
So LQG is a linear quadratic Gaussian controller, which is a very classical control approach that combines a state estimator with an optimal LQR controller. There are some great YouTube videos that I would really recommend if this is a concept that you haven't encountered yet, and I'll leave links to those in the description.
But I want to give a very, and the control people will not like it, but I will give a very informal answer, which is control is full of trade-offs. Co-design is the toolbox to deal with trade-offs. So that's an answer per se. You can study control problems with co-design. More specifically, when you design a controller, you think about all sorts of trade-offs. If you think about LQG, for instance, or LQR, there is this trade-off between input energy you use and the performance or the errors of your controller. There is, when you go to the inference part or the estimation part with LQG, there is also this idea of being robust to system noise and observation noise. Turns out all these things can be ordered, right? I can say I have worse system noise, worse observation noise than another system. You can, for instance, use ellipsoids or covariance matrices to represent these partial orders. And the partial orders are ellipsoid inclusions in that case. And now, designing a controller becomes a particular box where the task is you're given a certain trajectory to follow, maybe, and you want to be robust to certain noise, and now you want to minimize, for instance, errors or energy consumption. But the nice thing about co-design is that it allows you to put these controllers into larger schemes where now you interconnect them with other design decisions. So for instance, if the observations come from a perception algorithm, you interconnect these uncertainties to the perception algorithm performance. And now the perception algorithm is interconnected with a sensor, right? And the quality of the sensor measurements influence how the perception algorithm performs, which influence in turn how the controller reacts. And you can interconnect this with compute and start looking at problems of limited compute, or you can start looking at problems where you want minimality in your sensors. You can answer questions such as, what is the minimal set of sensors through which, under any control action, I can reach this performance in the controls? All sorts of things, right? So control, I think, is a very, very nice set of boxes for our framework.
So, as many of us are aware, optimization and trade-off is at the heart of control. And this is somewhat unrelated, but it did remind me of a conversation that I had with my current supervisor when I was just starting to learn about control. So he was always super enthusiastic about his teaching, and I asked him what he loved about control, and this was the exact reason that he gave. So he loved these trade-offs and the flexibility involved in designing control algorithms to deal with these. These trade-offs mean that control lends itself naturally to representation as a design problem within the co-design framework, allowing it to be optimized alongside all of the other system components. But it turns out that integrating controllers as one part of a larger co-design system framework is not the only reason why Gioele is so active in the control community.
The other reason why I believe control is kind of a nice case study is because in controls, people start to realize that architectures matter a lot. In fact, this is the topic of our workshop at the last CDC and this CDC, together with Aaron Ames and Nick Matney, control architecture theory, right? So there are architectures everywhere. You can think the very simple or very intuitive one is the one where you want to have some high-level plan, then some trajectory generator, and finally a low-level controller that follows that trajectory. So those are kind of a vertical architecture, but you might have all sorts of architectures, right? There's people like John Doyle studying architectures that describe how evolution happens, right? Or there's people in computational biology that study architectures for how very small systems interact together, right? So architectures are everywhere. And co-design gives you a very nice framework to reason about architectures. Why? Because composition is part of the nature of co-design, right? And so there are many interesting problems at that interface. The thing is, it's not, first of all, well, there is a superficial issue, which is control theorists are used to look at signal flow diagrams. And the co-design diagrams pretty much look similar to that, but it's not. Signal flow diagrams are diagrams where you have wires that are signals and the boxes are things that happen to signals. Co-design is the wires are quantities you care about and the boxes are relations, but these diagrams have no direction. It's just requirements, right? And so the first fallacy is to look at the co-design stuff and, but Gioele is just reinventing Simulink. No, it's different. And the other one is it forces control people to go out of controls. You don't assume a noise is given to you. You actually try to design the entire system. And I think that's great, especially these days where, we're going into structures where intelligent systems are more and more interconnected, but for some people it's out of the comfort zone, right? Because you just cannot work on your small control system. You have to work on the entire thing, right? So I think those are interesting times. And with this workshop, we're really seeing that there are so many people already using architectures, but we lack kind of the formalism to reason about them, which will be in part co-design, in part category theory. There's going to be many, many things to do that, but I think it's a very promising area.
I actually attended one of the sessions of the CDC workshop that Gioele mentioned on control architecture theory, and I think this was probably my favourite session of the entirety of the conference. I don't know whether this is just a topic I find particularly interesting or whether Gioele is just amazing at finding interesting people to present, but it was fantastic. If you're interested, you can listen to my insights on that and hear from a few of the speakers in the CDC episode that I released back in January.
So you mentioned LQG controllers. I know you've looked at a few other controllers. So I was kind of wondering, are there any controllers that you don't think would fit into the co-design framework, or could it be applied to anything?
Well, of course, the devil is in the detail, right? But it just depends on what you want to do with it, right? If you frame your control problem as you have to solve a certain task with a certain performance and pay this cost, you just have to make sure that there is some monotone relation between these two. But, most of the times there is such a monotone relation in expectation or so. It just depends on how you choose the wires. Maybe it's not always true that if I add delays to my system, my performance decreases. There are situations in which performance might be non-monotonically increasing, but that doesn't mean it cannot work for those specific systems. It just means for those specific systems, you want to reorganize your wires. I think I gave, I don't know how many talks about co-design now, probably 80 talks in the last couple of years. And a typical question or comment is, oh, but you cannot really, because obviously I go in a very cocky way and I say, oh, you can model everything with co-design. Co-design is the future. And people always don't like it, which is exactly why I do it. And people say, oh, for instance, you cannot model the Brest paradox. And I say, why? Oh, well, because in that case, you can show, do you know about the Brest paradox? So there is this very nice example in game theory where you're given a simple network and people can have to travel from one location to another location, right? And they are given some options. There are many variations. One is they can choose a road, a combination of a road and a ferry. And, there is an equilibrium of the entire system that makes sure essentially an equilibrium, first of all, I have to define what it means. Equilibrium means people have no interest in deviating from whatever choice they make. But whatever, you can study these equilibria and you can see that the equilibrium has a certain average travel time, say 60 minutes for every passenger. And now you add infrastructure to the system. For instance, you add a direct bridge that connects two locations and you resolve the same problem. You look at the equilibria and now the time is worse. By the way, this bridge, in most of the examples, the bridge is an instantaneous bridge. So it teleports you from one location to another. So it's an idealistic work. And so there is this paradoxon because you added the resources, in this case, if people that have this comment think of a wire of resources as being the number of edges in the network, but you made the average travel time worse. And that's a paradox, right? It's studied in game theory. And my answer would be, sure, that's a wrong co-design problem. But the really wrong thing is interpreting the number of edges as a resource, right? Or interpreting what is the law for creating the relation. Maybe the law for creating the relation is, please look at the equilibria of this problem as long as there are no paradoxes. If there are paradoxes, I don't know, choose something else, right? But I think there are many of these problems that in the classic way could look like not amenable to co-design, but up to some rewriting and rewiring at the end of the day work. So I still have to see something that cannot really be modeled with co-design. The question is rather, can it lead to some tractable formulations, right? Because if you are in the theory world, yes, I can prove I have co-design problems. I can reformulate the problem to make it into a valid Boolean profunctor, whatever, but it's going to be useful at the end of the day. That's the question, right? That's where we have a lot of open questions in my lab. And so I don't want to say, yeah, you can model control with co-design. No, that's not the case. But I think co-design allows parts of the control disciplines to now interconnect with other disciplines. And that's what I'm very excited about.
One of the other questions that I had that you kind of touched on there is, how do you decide what is a functionality and what is a resource?
Very good question. So we have, of course, once you start working with this, it's natural to you, right? And in many cases, it's natural. In the talks I give, I sometimes show this specification sheet for new drones. And there are things like for every technology, you have the lifetime, the weight, the granularity of the sensors they have, the cameras, whatever. And people pretty much already say, okay, lifetime is a functionality. The weight is a resource. The cost is a resource. I don't know. The quality of the camera is a functionality. So in that case, it's easy. In some other cases, it's not. The rule of thumb is functionalities are something you provide and typically want to maximize. Resources are something that you require and typically cost you. You want to minimize that cost. And that pretty much has worked so far. But we are in the process of writing the guideline of how to model co-design problems, and there's not such a thing, right? But to be fair, this is true for many other disciplines, right? For instance, there is a whole discipline of how do I make sure that my problem is a convex optimization problem? How can I reformulate it and make it into a convex optimization problem? There are many techniques that people nowadays use, but you needed many years of people playing around with applications and finding common patterns and so on. I think we have to go through that process with co-design now. It's us very new. It's essentially the group at ETH, my group now, a bunch of explorers, but it's not really mainstream yet, right? So I think we're learning how to do that better.
So we've talked kind of fairly high level about code design. Chapter 7 of your thesis focuses on actually solving the code design problem. Could you give a general outline of kind of how you do that?
Yes. So the query I was talking about, this fixed functionality mean resource, gives rise to a huge optimization problem. It's a problem where you have a multi-graph of problems. As I said, the nodes are the problems, the edges are the interconnections and the dependencies. You have all the constraints we talked about before, and the objective is to minimize resource consumptions at the system level. So it's a multi-component, multi-objective optimization problem. On top of that, you don't have any nice structure. So it's not convex, it's not differentiable, not continuous, not submodular, none of those nice properties. And if you know anything about multi-objective optimization, you know that these are bad news. Actually, the problem can be solved in a quite tractable way because of the compositional structure. So essentially, there is a theorem that says that you can solve the composition of problems, which is what we want to do, as the composition of the solution of problems. It seems like I'm just playing with words, but what it means is that you can solve each box alone and then compose them. And you can do that because there is a functor between the category of problems, this architecture of problems, and the architecture of solutions, meaning there is a way to go from one way to another in a constructive way. And this is great because it means that, first of all, you can build an algorithm. This algorithm is a special fixed point algorithm that has a guarantee to converge to the optimal solutions or gives you a certificate of infeasibility, right? I want to buy back in Boston in 1 hour from now, infeasible, right? No matter how much you want to pay, infeasible. But the second more important property is that the complexity of solving this problem is only linear in the number of options you have in each box and not exponential. And that gives us hope, right? Because we're going to build huge networks of problems and you don't want your complexity to explode combinatorially. The complexity actually depends on the feedback, the size of your feedback loops, which is kind of the irreducible complexity of the design problems. Now, this is the nice theory, and in the thesis we have some examples, some characterizations, and so on. Long story short, though, my vision is to bring co-design everywhere to solve huge problems, and we are not there yet. So a lot of what goes on in my group now is how do we make this scale even better, right? For instance, in the cases in which you assume more structure in your problems, can you exploit the structure to solve it faster? That's one area. Another area is, sure, the complexity is linear in the number of options, but sometimes getting these options in the first place, it's very expensive. Say a special feasibility relation is given to you by an expert in a certain field, and you have to wait for them to reply to your email. Or maybe you have a simulation that runs for, a week. Or you have to solve an optimization problem to get a special pairing, or you have to run an experiment. Ideally, you don't want to pre-compute these solutions without knowing exactly what they are needed for. You would like to have a framework that, given us some functionality specification, automatically samples these boxes. So this is, in my lab, we have a vertical, which is kind of adaptive sampling or sensitivity analysis for this new class of problems. So this is how the solution actually works.
Okay, so as well as lots of very impressive theory, your thesis also presented kind of applications of this framework. So you mentioned mobility on demand systems a bit already. So could you give an overview of how these types of systems can be transformed into a co-design problem?
Yes. So first of all, there are some strategic reasons, but they just happen to be. The first one is I was very passionate about the technology, autonomous mobility, and I wanted to see the impact on larger systems. But then I really needed something that not only allows you to talk about multiple components in an horizontal way, which could be the design of a single vehicle, but also I needed these vertical abstractions where you have multiple scales. I have a vehicle, I have a fleet, the fleet has to interact with the network, and everything has to interact with the municipality, and so on and so forth, right? And I think the autonomous mobility on demand, or so-called intermodal systems, was a very good example. And so how do you model this as a co-design problem? This is a huge co-design problem where there is the design of each option, each mode. So imagine you're designing micromobility and you want to design the actual scooter, or you're designing autonomous vehicles, you're actually designing this single autonomous vehicles, and then you're designing the single train, how the train will look like, and so on. Then there's going to be the design of the fleet, which could be uniform or heterogeneous, right? You want a fleet of e-bikes, e-scooters, these kind of things. You could have a fleet of autonomous vehicles, depending on what you want, and the fleet of trains or the schedule of the trains. You want to design the network on which each of these modes operates. So you can think of this as a multi-graph with some labels on the edges, for instance, the travel time, the cost, the energy consumption, and so on. And finally, you want to design how you will orchestrate the system or how you will operate them. And this is in the realm of operations research. For instance, in autonomous mobility on demand is like, how do I assign passengers to vehicles? How do I route the vehicles? How do I rebalance vehicles to new locations to be proactive and find new passengers? For trains, it could be, how do I optimally allocate my resources to create schedules that serve the demand? And for micro-mobility options, it could be, where do I place the charging stations or the stations where these scooters actually are? And so this is a huge interconnected system where all the steps I described so far influence each other.
So co-design is involved in all aspects of mobility on demand systems, from designing each of the components of a particular vehicle all the way up to decisions about how the system operates on a citywide level. If you want to learn more about how this all works mathematically, I encourage you to either go read Gioele's papers or chapters 11 to 12 of his thesis, because there are some really interesting details that we've skimmed over here.
But the final goal is what? Is to serve some demand with a lot of uncertainty. And then what? Depending on what you care about, could be to minimize the investment you have to put in the system as a municipality, to minimize the travel time, but it could also be to minimize emissions, right? Or you might want to not only minimize the travel time on average, but you want to minimize inefficiency or inequity in the travel time allocations, right? Because if you minimize average travel time, there might be, on average, people are happy, but then there might be some people that take 4 hours to do a simple journey, right? All these things, right? And at the end of the day, the task is really, you fix some demand, and now you find these trade-offs between, for instance, investments and average travel time or some metric like that. And every point on this huge Pareto front will be a combination of the best vehicle design, the best fleet size, the best fleet composition for each mode, the network on which they should operate, how they should interact with other services. And so you get some sort of policy recommendation. Of course, we are far from directly implementing those solutions, but I find that by interacting with a lot of municipalities, I find that having this sort of visual trade-offs where they can play around with parameters, see what happens when they change a parameter, see what the solutions suggested are, they can actually start interacting more with the system. And to give you a sense, the status quo for a lot of these problems is to go to Boston Consulting or these famous consulting companies. You pay a lot for their credibility. They come back to you with one solution, no interpretation, and you cannot really, it's not really intellectually tractable in that sense, right? It's fully tractable because if something goes wrong, you say, look, these people are very credible and I trust them. But it's not really, it violates a lot of this vision I have for systems engineering of the future.
Gioele is about to give a few more examples of applications where he's implemented co-design, but I wanted to chip in with a few more that he doesn't mention that I think are really cool. So firstly, there are a few papers he's collaborated on that apply co-design to Formula One, considering the design of the vehicle as well as the racing strategy, both in a single race and over an entire season. This was actually the first paper of Gioele's that I read when it was suggested for my journal club, and I would definitely recommend it if you're interested in Formula One. The second application is soft robotics, and I mean anything that could be applied to soft robotics I'm already obsessed by, but Gioele worked on a review paper that was titled Soft Yet Effective Robotics via Holistic Co-Design, and this looked at how to jointly optimise both the morphology and control algorithms of a soft robot, as well as how to formalise the trade-offs between safety and performance. If you've listened to the In Control episode with Cosmo Della Santina, you'll have some idea of the complexity of designing and controlling soft robotics. And actually, Cosmo was a co-author on this paper. So that's 3 interesting examples of co-design. What others are there?
Now we are doing a lot of work in multi-agent systems in general, so you can scale all of this into multi-agent robotics, where you now have a task and you want to create the best fleet for this for solving this task. Without biases, I want to cover an area in a warehouse, design the best robotic fleet. And an answer might be that you have humans, or you have fixed sensors, or you have a bunch of ground robots, robo-bees and drones, but it really depends. And we essentially want to understand what are the trade-offs in these design choices. Another thing we're interested in is how do you connect this large mobility co-design problem with other smart city problems. For instance, energy, right? A technology such as autonomous mobility on demand will drastically change how energy systems are used today. Why? Because first of all, right now when people have electric vehicles, they typically use them at very predictable times. They go to work in the morning, come back in the evening, they charge whenever they are home or they're at the office, and so on. Autonomous mobility on demand will, on one hand, reduce the number of vehicles on the road, if you think about the full adoption, but also will use these vehicles constantly. And so people will have to decide when to charge and so on based on the companies will decide mostly based on their utility. And that will change a bit the energy consumption and maybe designing where to place charging stations, how to operate them, how to redesign the spaces that are now used for parking that will not be used anymore, how to do that. So there are a lot of problems that take this huge transportation problem and interconnect it with auxiliary services, right? And I think that's very interesting, and I'm kind of looking forward to exploring more. So far, my applications have been mostly limited by my own expertise or interest. But the nice thing about having a group is that now students have their own drinks, right? And they go and apply the tools to whatever. I have a student now that is looking into water systems in New York. They have a contact with the city of New York to essentially look at what happens when it rains too much and so on, and how to use some of these tools to proactively design policies to go and save some metro stations, right? Because the metro stations are flooded most of the time, and that creates a lot of damage. And in New York, they don't have enough personnel to actually go and close and secure all the stations. And now you want to find out which ones to secure based on the connectivity and so on, right? This is an example of an application that I would have never thought about. And now actually it's possible because of the co-design stuff. Another application is I'm running this class on co-design, and at the end of the term, students work on projects. And now undergraduates at MIT were really unhappy with the canteen situation or the dining hall situation. And they were using co-design to redesign the menus, the ingredient supply, and kind of things. So I'm really impressed by how many new applications we can find.
So the final technical part of this interview, I wanted to ask you a bit about game theory.
Yes.
Because you presented some kind of preliminary work on integrating co-design into game theory. So yeah, could you just talk a little bit about that?
Yes. So first of all, there is inevitably everything I talked about so far leads to applying these to huge systems where, sure, you have multiple components, multiple systems, multiple stakeholders. But when you start talking about multiple stakeholders and multiple objectives, you cannot assume they will be aligned. And in fact, in the transportation example, when we were discussing about the objectives, what is the objective? Is minimizing investments, minimizing emissions, minimizing travel time. Already these three objectives highlight three different players, right? In a sense, maximize the return on investment is the private mobility providers. Minimizing travel time could be thought of as the citizens, and minimizing emissions could be thought of as the municipality, right? So the long-term vision we are developing in the lab is develop a theory of co-design games. But it's not as easy as it sounds because, these new optimization problems are very exotic, let alone the game theory version. The game theory version is different people control different boxes. They have different objectives, and they don't necessarily share what they care about. They're only constrained by the interactions of the boxes. And so we started working on this notion of partially ordered games, which is the first step, is essentially games where players have partially ordered objectives. Because that was the first hurdle. Like people are not used to think about multiple objectives, multiple trade-offs. They always think about the real numbers. So that was the first thing. And we applied this to motion planning. Then another line of work we started doing, and actually a student of mine, Minja, is presenting later this afternoon, is to think about hierarchical games. Another big aspect of co-design is that you have these hierarchies. And a hierarchy that naturally arises is the one, in mobility, is the one of you have a municipality that sets some rules. There are mobility providers that actually interact simultaneously, reacting to these rules. And finally, you have citizens that travel depending on whatever actions happened before. And you can study this with Stackelberg games or the so-called multi-stage games.
A Stackelberg game is a sequential game where players take on the role of either a leader or a follower. For more information on traditional game theory, I refer you to last month's episode with Barbara Franchi, where we go into some key concepts in more detail. Also, one of the recent In Control episodes with Jeff Sharma covered some very interesting links between game theory and control.
The issue is that to model these things properly, this doesn't fit any classic Stackelberg game for which you have nice properties of existence of equilibria, convergence of algorithms, and so on. So essentially, we have to redevelop tools to actually solve these problems in a tractable way. We have some recent work on using some model-free approaches to deal with this. But yeah, the game theory is a big aspect of my research group now. But there are more challenges than solutions yet. So it's really a growing field in my research group.
What do you think of the outstanding challenges or kind of limitations of the current co-design theory?
Oh, there are not limitations that I don't think we can overcome. But the biggest limitation is that we are so ambitious that we want to apply this to huge systems. And there is a big limitation on, first of all, we have to learn to go and spread the word. We have to learn about these applications and understand how to model them. And that takes a lot of time. And then it's the complexity of solving these problems. So a lot of my work is about solving these problems in a more efficient way. And you have to imagine we have to develop all the algorithms and the sensitivity analysis and the optimization tools for this new monster class of problems. I think those are two big challenges. But it's not, as I said, maybe it's just because I just started the lab last year and I have resources and I have great people. I don't think you cannot overcome those. It's just a matter of time. But yeah, those are the biggest challenges, I think.
Are there any systems you haven't applied the co-design framework to yet that you think could really benefit?
Oh yeah, everything that has multiple components. I think a very promising area we are exploring is aerospace. There is a rich tradition of applying systems engineering tools. You have to design parts of the mission, the specific robots or the specific drones. So that's one. I think going back and revisiting some of the early work done by other people in embedded systems, for instance, chip design, these kind of things could be another important one. But right now, as I said, I'm more limited by, to do this well, you need somebody to really be passionate about the subject. And so I'm relying on the students that say, okay, I love chip design. Let's do it. A very promising one is I have a PhD student that started with me this year, Vincent Abbott, and he's using the co-design framework to design deep learning architectures. So he's going even a level down, saying, okay, can I design the entire algorithmic architecture using co-design by being aware of parallelizations, depending on the hardware I'm given and so on, right? And that's giving some nice results. So that's a kind of an unexpected application that I think could be very interesting.
Okay, so quick fire questions at the end.
Yeah.
What's the best piece of advice you've ever received?
All right, so the more you grow into the academic life, the more you will receive advice. The hard part is understanding who, okay, I'll make it short. The best advice is choose which advice you want to follow. So it's a meta advice, essentially. Beware that you will receive a lot of advice. Choose your own advice.
What's your favorite part of your job?
So there are so many. Essentially, during the PhD, I discovered I wanted to be a professor, but then I thought it wasn't it was a unilateral love, in a sense. I thought I will never get a job. Then I got a dream job. And there are many things. First of all, you interact with students every day. I love to meet with them for hours. You talk about things. You learn from them and you see them grow. Like my students, like the older students are now 1.5 years old. Like I started 1 year, 4 months ago. But you already see a huge difference in the way they present, in the way they think. So that's super rewarding. But also just a basic, productivity. Like you have an idea, you talk to a very good student, they make it theirs, they actually give it a new spin, and you do things that you wouldn't be able to do in the same amount of time. So that's one aspect. The other aspect is freedom. I was really underrating how free you are as a faculty. Essentially, yeah, sure, you have to teach, you have to do your service work, your committee work, you have to publish, but that's all pleasant things. But then apart from that, nobody cares about where you are, what you do. You can think about problems. Sure, there is tenure. I'm aware that it's a stressing process. But on the other hand, I can do whatever I want. If I now say I want to study, quantum mechanics, I could do that. Nobody prevents me from doing that. So there's a lot of freedom and flexibility. You can work from home, you can work from another country, you can travel a lot. Like we are an example, we are in Rio de Janeiro talking and discussing on a podcast. Like this is the dream job, I think. And maybe the final thing is, these days I feel you can have an impact on society. And some people might laugh at that because these days it's almost the other direction, right? People start saying, oh, with the AI, the role of academia is unclear and so on. But, when you teach classes, when you see undergraduates and graduates growing, I feel you're leaving a trace in a sense. And that's a part I discovered being very important, and I actually love it as well.
Who's your role model within either control, design, optimization?
Oh, there are so many. Here is the classic, at the Oscars when you don't want to make someone unhappy. All right, so a first name that comes to mind is people like Alberto Vincentelli. He was in controls for a while. I don't think he would consider himself in controls, but he's a role model for many things. First of all, he's huge, super energetic. I think he's about to be 80 years old, but he still runs marathons. He still teaches at Berkeley. He's in so many boards of, he's a board member for many companies. He travels all over the world. So he's the dream of how I want to be when I'm his age. And actually, in fact, I feel old when I meet with him because, to tell you an anecdote, I had him over for dinner a couple of months ago in Boston. He came and said, I just ran 10 kilometers. I just came from Europe on a flight. He was very happy to do the dinner. The morning after, he was very fresh into his meeting. And I just live in Boston at dinner with him. And the morning after, I was not functional, right? So, yeah, jokes aside, scientifically, is a great example of how you don't have to trade off academic performance and industrial performance when you want to do both. He's a great example of, he founded some of the greatest automated chip design companies, Cadence, Synopsys, worth billions of dollars. He never stopped being a faculty at Berkeley, still mentors students. Students are under his supervision are great, and he made the best of both worlds. And I think he fully embraces, when I think of a professor that has achieved both industrial translation, but also academic excellence, I think of him as an example.
If you would like to hear more about Alberto Vincentelli's work in more detail, he's featured in a 2-part episode on the In Control podcast. It took over 3 hours for him and Alberto Paduan to cover the extent of his research career. That is how much this man has achieved.
There are many others, right? Emilio Frazzoli, my advisor, is really a big role model. It's fun how these people, you get to work with them for the science, but then they become friends and you consider them part of family. And then you ask them for advice about life, right? This is really one thing I like about the controls community. There's a lot of family, even more than colleagues. Another one is John Doyle. I don't think he needs an introduction, but a big influencer in the game. Maybe younger ones is when I started looking at category theory things. Aaron Ames was a big name because he, essentially wrote his PhD thesis in looking at category theory things, and he gave me hope that, of course, this is not hot yet, but if people like him that now are super accomplished did that and it was useful, probably it's going to be useful. So, yeah, there are so many, but I'm sure I'm forgetting things, but these ones are the ones I wanted to mention.
Final question, what's been your favorite paper or project to have worked on?
Okay, I'll leave you with this. I want to share a state of mind. I'm so excited every day about what I do now. It's getting exponentially more exciting. That's the next paper I'm writing. So I don't think I reached that peak yet. There are many cool papers we are writing, but every day I'm more excited. So that's the next one. I'm sorry, it's not it's not.
It's good. It's a unique answer. I like that. Yeah, thank you so much for the...
Thanks so much, Lucy.
So, in summary, co-design is a general framework that allows you to model and optimize large interconnected problems. It allows you to deal with multidisciplinary trade-offs occurring at multiple levels of abstraction in a coherent and mathematical way. It does this by formulating subcomponents into individual co-design problems that could be interconnected to form the entire system, and it uses tools from category theory to make this mathematically rigorous. This allows it to represent a wide range of different systems, including but definitely not limited to mobility on demand systems, multi-agent robotics, Formula One racing, soft robotics, deep learning architectures, aerospace systems, and chip design. I hope you've enjoyed this episode. I absolutely loved learning about the co-design framework, and I'm very happy that I got to share it with all of you. You can let me know what you think via LinkedIn, where you can follow the podcast or connect with me directly. In the next episode, I'm going to be talking to Brian Douglas, who you probably already know from his MATLAB Tech Talks or Control Systems Lectures YouTube videos. We're going to touch a little bit on his YouTube career, but mostly focus on what it's like to be a control engineer in industry. That'll be released on the 1st of April, but until then, I hope you have a fantastic month.